Welcome to section 4 of part 2 of the Contact Manager project. We begin today working on what we call the insertion sort. So previously we went over the selection sort algorithm. We're going to look at a new algorithm and measure its efficiency after we've put in the code for it. So let's begin by looking at how the insertion sort works, and if you navigate to the website, you can click on the insertion sort animation link, which will take you to this web page, which I think does a fairly good job of demonstrating how the insertion sort actually works. So here we have a list of unsorted numbers, and we're going to start by taking out a number, the first number in the list, and then we're going to insert that back into the list in numerical order by following a series of steps. First, we're going to ask, is this the correct position for 86? Well, does 86 come after 57? It does, so we're going to go to the next step, which is to insert it. And then we're going to look and say, is this list in sorted order? So, do I need to continue? Well, if I look at these, I can see that I've got, 57, 86, 91, but then I've got 7, and it is not in the correct location, so I'm going to need to go back to the step where I take out 91 and figure out where I'm going to put it. Well, is it going to need to go in front of 57, 86? No, it's going to go back into position where it was. It's in the correct position, so we're going to insert it back, and then we're going to move on. Do we have to continue sorting? Well, 7 is not in order, so we're definitely going to have to continue sorting, so we're going to go back up. We pull out 7, and now this is where the insertion sort actually gets its name. In order for 7 to go in this list, and notice that what we're doing is we're sort of constructing two sublists here, or two areas within our list. All the elements in green have been sorted. All the elements in gray have yet to be sorted. So what we're going to do is compare 7 to 57 and say, is that the correct position? It's not, so we're going to move 91 down. Then we're going to say, does 7 go in this slot? It does not. Is this the correct position? No, so we're going to move 86 down. Then we're going to go and look at 57. Is this the correct position? Should it come after 57? No, it should not, so 57 gets moved down. And then, are we now finally at the correct position? Well, we're out of position, so it must be the correct position. Okay, do we want to continue this? Well, 65 is not in order, so we're definitely going to have to continue. We take out 65. Now, does 65 belong before or after 91? It does. It belongs before 91, so we're going to move 91 down to make room for it. Then we're going to compare it to 86. Well, 86 has to move down. And this is where the efficiency of the insertion sort comes in, because notice our inner loop is going to get to stop after just 2 passes here, because we found the place where we can insert 65 into the list. Then we get to 22, which is going to have several elements inserted. There we go. And we're almost there. Are we going to insert it or move the 7? We're going to, of course, insert it. All right. And we're just about done. At this point, we're just going to play this so you can watch. The 47 is going to get moved. It'll eventually get inserted into our list. And then, when we're done, one more element to insert. And we are going to be left with a fully sorted list. So now we need to make some code that can accomplish these tasks. So what we're going to do is we're going to shrink this window over here, because we may want to come back to this as we are going through our code here. We're going to go back to our code, and here we had our insertion or selection sort. What we're going to do is we're going to add a new method above the selection sort here. So we're going to add a public static int insertion sort. Well, let's try and spell it right. That's also going to take a list of contact. That's going to be contacts, okay. And then just like before, we're going to start by having our iterations variable set to 0. And when we're done, we're going to return our iterations so that we know how many passes it took to sort a list. Because once again, we're going to be measuring efficiency by counting how many iterations of loops we have within this method. All right, so what do we need to do? Well, first, if you think about what this overall process did, it had to go through each element in the list to figure out where to put it. Okay, so if we were to generalize the process here, we have to start by going through almost the whole list, starting with the second element, and we're going to be going backwards through our list instead of going forwards. So this is going to be slightly different than the animation. So what does that look like? Well, what we're looking at now is this step here, this outer loop. See this loop right here? We're doing this outer loop where we're taking out what they call a card. In this case, for us, it's a contact. So first we have to do our loop. So we're going to do for int current element, which is the element that we're going to be sorting, is going to start out with a value of 1, and we're going to do current element is less than contacts.size, and then current element plus plus. And I just realized that I made a horrible mistake here. I said that we're going to start going through almost the whole list, starting with the second element. I said we were going backwards. I misspoke. We're not going backwards. We're going forward through the list, just like it showed in the image here. I am terribly sorry for misspeaking. Okay, so let's go on to our next step, which is this taking out of the card. Well, how do we do that for the purposes of our array here? We could do that. We're going to say take out the element and store it for later. Okay, now in our case, we're not actually removing it. We're just going to get a reference to it. So we're going to say contact, the element that we're going to be inserting is equal to contacts.get the current element. Okay? Now you might ask yourself, why did we start with 1? Well, the answer is, and if we reset this and we look at what it does, notice that we skip the first element because the first thing we're going to do, let's do reset here, is we're going to take out the first element and then see how it compares to the element that's right before it in the list. So since we're starting with the first element, or the second element, and comparing it to the first, we set our current element index to 1. Okay? All right, and then what we have to do is we have to calculate what we're going to call our shift index. And that's going to be equal to the current element minus 1. Okay? So what this is we're going to, oops, I should put that up here. What we're going to do is we're going to prepare to compare all the elements that precede the current element. And this is where we're going to be going backwards. Okay? So what we're doing is we're looking at the elements that come before the current element. So let's look at that again in the animation. We pull out the current element, Okay, that becomes our insert element in our algorithm. And then we're going to compare it to this element. Well, does it need to be inserted before 29 in this example that's currently on the video? Our numbers have changed here, so yes, it does. So then we're going to insert it. That's going to be what we're going to do very shortly. So what we've done here is we've calculated our shift index for a first time through the loop. That will start out being 0. And then we're going to say, while our shift index is greater than or equal to 0, and this becomes our inner loop, which is this tight little bit of code here. They don't really show it as being a loop, but this is comparing our current position and then doing a move. And since this is our inner loop, since this is the inner loop, increment the iterator. So we just write iterator plus plus. Okay. Now what we have to do is get the element. Oops, I misspelled iterator. Iterator. There we go. We have. Oh, sorry. Iterations. There we go. Now we need to get the element. Get the element that we might have to shift down from the list. So how do we do that? We say contact shift element is equal to contacts.get shift index. So what we're doing now is, in this example, we're pulling out the 29 so that we can insert the 15 in front of it if we need to. This becomes the element that we might shift if it becomes necessary to move to make room for the insert element. Well, how do we decide if that's necessary? So, are they already in order? If so, abandon the inner loop. This is a critical step for this algorithm because this is really what saves you so many iterations. So what does it look like? We say if the insert element dot, we have to get the last name first. Oops, dot get last name first. Dot compare to, because we're comparing two strings, the shift element dot get. Whoops, no, not get address. Shift element dot get last name first is greater than 0, then it is not necessary to swap these elements. And as soon as you find a spot here in the list where it is not necessary to do an insertion, you get to stop. So watch. These elements are already sorted in order. So the first thing that's going to happen is 64 is going to get compared to 29. Because it doesn't need to be shifted, 64 could go right back into this slot. I get to stop comparing without doing any other comparisons. But watch what happens when we do 10. When we do 10, we have to make a shift down. So that's what we're going to do next. But right now, what we're saying is if I realize that all my elements are already in order at this point, I can break out of my loop. Now, there's a couple ways to do this. The other way to break out of this loop would be to alter the shift index, but in this case that will break out our algorithm because we need shift index to have the correct value. So break is really our only option, writing the algorithm this way. Okay? All right, so now we're down here. What do we do if they aren't in order? Well, then we shift the element one slot to the back of the list. How do we do that? Well, we do that by saying contacts.set shift index plus 1. And what do we want to put there? We want to put the shift element. And what are we doing with this step? We're doing this action right here. We're moving 64 down a notch. Then we're moving 29 down a notch. Then we're going to move 15 down a notch. And that's going to bring us to this point right here. Our shift index is no longer greater than or equal to 0. So our loop is going to end here. And now we have to do our final step. If they aren't in order, or the beginning of the list is reached, let's see, we need to put the insert element back in the list. So how do we do that? We do contacts.set, and we do shift index, let's see, +1. But this time, what element are we putting in? We're putting in the insert element. So what does that look like in the animation? That looks like this step right here. Watch, the 10 is going to be put back into this list. Now, what does that look like when we do a number that's already in order? Well, both 73 and 91 get pulled out and then get put right back in. What does it look like when we get down to 49, though? We have to make some room. We shift 91 down, then we shift 73 down, then we shift 64 down, and then now we've got the right spot to insert, and we're back at this line of code right here. This would be line 31. We would be stepping and putting 49 into its slot. Okay, and let's see. Our next step is, oh, I left out one important step here. Sorry. The last thing we need to do is we need to decrement the shift index moving towards the front of the list. I left out a very critical step here, which is shift index minus minus. This is back inside the while loop here. Remember, the whole point is we're doing this. We're comparing all the elements that precede the current element, going backwards through the list. If I left this little line out, I wouldn't be going backwards through the list. Okay? So, you know what? This is not a very good description of what we're doing here. What we're doing here is we're saying we've located and made room in the list to place the insert element. Yeah, I think that's a better description of what's happening at this step. Once we get here, we've located and made room in the list to place the insert element in its sorted order. Okay? All right, so we've got this code written. What do we need to do to test this? Well, first let's go ahead and test this with 500 elements. And this time we're going to change this to be the insertion sort. And then we're going to actually print the contacts so we can see what our source list looks like. You know what? Let's start with 5 contacts, not 500. We want something a little bit more manageable to see if our routine is working. Okay, so we started with Redding, Newbie, Bowdoin, Fu, Wong, and then we got Bowdoin, Fu, Newbie, Redding, Wong, which seems like it's in order. Yep, okay, and it took 7 iterations to do 5 items. That's not too bad. That's nearly a 1-to-1 ratio. Now let's take a look at what happens if we do our list in sorted order. So it's ascending order with 5 items. Look at that. We actually beat a 1-to-1 ratio. Our list is sorted in 4 iterations. That's less than the number of elements it took. Why is this method so fast at sorting a list that's already sorted? And here's what it amounts to. It goes into, oops, that should be abandon. Wow, that was tough to spell. Okay. Because this line right here breaks out of the inner loop anytime it finds an element that's already in the proper location. And so that saves us a lot of iterations for a list that's already in order. How about a list that's in the worst possible order, which is a descending list? Well, now we get 10 iterations. So let's see how this compares to our selection sort. So we're going to start with reverse order, and we're going to do 500 elements. And it gave us 124,750. So let's go ahead and put that in. Oh, that looks familiar. 124,750. Well, that's exactly the same as the selection sort. I wonder if it'll be the same if we do 1,000. Let's run that. 499,500. Let's check that. Look at that. It's the exact same number. Well, so far, this doesn't seem like this is much of an improvement, does it? But now let's go ahead and change these back to 500, and let's do our optimal order test. And we already know this is going to be much better. Oh, 505 iterations. Well, that is far less. So let's go ahead and put that down. 505. And then while we're at it, let's change it to 1,000 and see what we got. 1,014. That's not bad at all. Okay, and I wonder what it'll be for an unsorted list. So let's try that. We run that. 63,416. If I run it again, am I going to get the same number? Because it's a random order, I'm not going to get the exact same number. I got 60,195, which is roughly half. 195 seems to be roughly half what I got for my selection sort. So that certainly seems like it's an improvement. And then it looks like that's 258,000. That's 252,000. And that's 249,000. So I'm going to go with that last one, just because it seems like a nice number. 249,041. Okay, so we can see that for a random ordered list, it seems like this is roughly twice as efficient. For an optimal ordered list, it is way more efficient. It's a nearly linear algorithm in terms of sorting an optimal list. And then for a reversed or worst case list, it's no more efficient. So you're going to go ahead and graph the rest of these and see how those curves play out. Fill that in, and then in your notes here, you could start to fill in now. We want a description of how a selection sort works, a short description of how the insertion sort works, and then notes about what makes them better and worse in certain conditions. And I'll give you a hint here. There's one case where the selection sort can actually be more efficient than the merge sort and the insertion sort, but it's a very specific, very rare case that we'll talk about much later. Okay, do your homework.